You know, we've all heard that green tea is one of the healthiest things you can possibly drink. It is absolutely packed with these powerful compounds that are supposed to be amazing for us. But here's the catch, the secret that almost nobody talks about. When you drink it, your body might not be getting any of the benefits you think it is. And that is a huge problem that scientists are now trying to solve with some seriously cool high-tech solutions.
Okay, so let's just take a look at this. This slide really lays out the incredible promise of green tea. We're talking connections to everything from antioxidant and anti-inflammatory effects to maybe even fighting off cardiovascular disease. And the magic ingredient behind all of this? A group of powerful plant compounds called catechins. These are natural antioxidants, but as we're about to find out, just getting them into our bodies to do their job, well, that's the real challenge.
And right there, that is the million-dollar question. You could drink gallons and gallons of green tea, but if your body can't actually absorb and use those amazing compounds, are you really getting any of the benefits? This whole problem has a name. It's called bioavailability, and it's the mystery we're going to unravel today. So here it is, the big catch. Those powerful catechins, especially the most important and potent one, it's a mouthful, called epigallocochin gale, or EGCG for short. They are notoriously difficult for our bodies to absorb. Just because you drink them doesn't mean they actually get into your bloodstream to do all that good work. This fundamental issue, this barrier, is all about that key term, bioavailability. So let's break that down. What is bioavailability? It's pretty simple, really. It's not about how much you consume, it's about how much your body can actually use. If something has low bioavailability, it means most of it is just passing right through your system without having any real effect at all. So just how low are we talking about here? Well, get ready for this, because it's pretty shocking. One study in rats found that the bioavailability of that star compound, EGCG, was a staggeringly low 0.1%. That's it. 0.1%. Because it's such an unstable molecule that gets totally broken down in our gut, 99.9% of that powerful antioxidant was essentially wasted. And check this out. This is a fantastic way to actually see the problem. Look at that middle graph for oral delivery. You get this tiny, quick spike of the stuff in your blood, and then poof, it's gone almost immediately. Now, compare that to an injection on the left, which is way more direct. The whole goal of all this new science is to get something that looks like the graph on the right, a nice, steady, sustained level in the body. Okay, so if the gut is the problem, what's the solution? Well, the first approach scientists are taking is pretty clever. Just bypass the gut completely. And that brings us to our first amazing solution, transdermal delivery. In other words, getting these powerful compounds directly through the skin. And this side-by-side really spells out why a skin patch could be such a game changer. On the left, with oral delivery, the catechins get hammered by stomach acid, and then they have to go through the liver. This is called the first pass effect, and it basically neutralizes most of them. But the patch on the right, it avoids all of that chaos, delivering a steady, controlled dose right into the bloodstream. The goal? Much, much higher bioavailability. But here's the thing, getting through our skin's defenses is no walk in the park. Our skin is literally a fortress. As you can see in this cross-section, it's got multiple layers. You've got the tough outer epidermis, which is the main wall, the dermis down below where all the blood vessels are, and then the deeper subcutaneous fat. To design a patch that actually works, scientists have to figure out how to engineer a way to sneak past all of these protective layers. Now, the biggest hurdle of all is that very, very top layer, the stratum corneum. And this brick and mortar analogy, it's perfect. The skin cells are like the bricks, and the lipids, or fats, between them are the cement holding it all together. It's an incredibly effective wall for blocking things out, so any transdermal technology has to be really smart to get through it. So how in the world do scientists actually breach that brick wall? Well, let's pull back the curtain and go inside the lab to see the fascinating process of building and testing one of these high-tech patches right from scratch. It's a really precise four-step process. First, they have to get the raw catechins out of dried green tea leaves. Second, they have to purify that raw extract to isolate just the key compounds they want, like our friend EGCG. Third, they take that purified good stuff and load it into a specially designed high-tech membrane. And finally, of course, they have to test the whole system in the lab to see if it actually works. And this is where it gets really cool. You can actually see the science in action. On the left is the basic chemical extraction, but the proof is on the right. That huge, sharp spike labeled EGCG,
That comes from a technique called high-performance liquid chromatography, or HPLC. Think of it as a super precise molecular filter. It confirms they've successfully isolated a pure, concentrated dose of EGCG, separating it from everything else, like caffeine. So this diagram shows us what happens next. The purified catechins get loaded into a polymer membrane, that's the heart of the patch. Now to test it, they use this device called a Franz diffusion cell. They place a piece of porcine, that's pig skin, which is a fantastic model for human skin, right between the patch and receptor fluid. Then they just measure how much of the catechin actually makes it through over time. And the results from these animal studies are, well, they're just staggering. The key number to look at here is AUC, which stands for area under the curve. It's basically a score for the total amount of the compound that got absorbed into the bloodstream over a period of time. For oral delivery, that score was about 34. For the transdermal patch, over 356. That is a more than 10-fold increase in total exposure. This isn't just a small improvement, it's a total game changer. So skin patches are one incredible solution. But hey, what if you still want to get these benefits from the foods and drinks you actually consume? Well, that brings us to our second solution, which tackles the exact same bioavailability problem from a completely different and much, much smaller angle. This technology is called nano-encapsulation. The best way to think about it is like creating microscopic armored cars for the catechin molecules. We know EGCG is super powerful, but it's also incredibly fragile. It gets destroyed by heat, light, and especially our own digestive system. So, nano-encapsulation wraps it up in a tiny protective shell, letting it survive that hostile journey through the gut and arrive safely where it needs to do its work. And what's amazing is that scientists have a whole toolkit of these nanocontainers. As you can see here, you've got different structures like nanocapsules, nanospheres, and liposomes. They're often made from things like biodegradable polymers or lipids. And the really clever part is that each one can be engineered to release its cargo only under specific conditions. So you could design a capsule, for example, that only dissolves when it hits the less acidic environment of the intestines. It's like a tiny, targeted smart bomb for nutrition. So after all of this amazing science, what does it all mean for the future? For our food, for our health? Well, it's about a lot more than just getting more out of our green tea. We are really entering the era of functional foods, everyday products that are engineered for specific health benefits. I mean, imagine bread that's fortified with nano-encapsulated omega-3s that don't taste fishy, or a juice where the vitamin C is protected, so it's just as potent on the shelf as it was on day one. This tech could totally revolutionize nutrition and maybe even how we deliver certain medicines. But of course, as this technology moves out of the lab and into our lives, it brings up some new things to think about. As this chart shows, nanomaterials can get into our food chain in a lot of different ways, not just when they're intentionally added, but also unintentionally from things like advanced food packaging or processing. This exposure means we have to start asking some very, very important questions. The potential here is absolutely incredible to finally unlock the full power of some of nature's best compounds and build a healthier future. But as we gain this awesome power to engineer our food at the molecular level, the big question remains, how do we balance the immense promise of this technology with the critical responsibility to make sure it's safe, for us and for the planet? The answer to that is going to define the future of what we eat.